geothermal, defense, and space exploration have a lot to learn from one another. In geothermal, we aim to accurately predict where geothermal resources are and find ways of economically drilling hotter and deeper. But in deep space exploration and hypersonics research and development, advanced materials have been developed to perform reliably at temperatures far exceeding those encountered in geothermal operations. So, can the advancements we need in high-temperature electronics and telemetry systems, high-temperature energy storage devices, advanced seals, coatings, and insulation materials be transferred into geothermal drilling from space and defense programs? What benefits can defense interests reap from geothermal's baseload capability, security, and resilience? And could geothermal energy power extraterrestrial exploration? Let's explore.
Hi, I'm Ken Wiesian. I'm a geothermal geophysicist at the Bureau of Economic Geology at the University of Texas at Austin. My work is mainly in the area of resource mapping, modeling, sensors, and project development. And I'm thrilled to be moderating this panel today. It's going to be one of the more wide-ranging panels with a very diverse set of backgrounds talking about technology transfer and collaborations. Besides my work as a scientist, but also relevant to this panel, in my previous life, I was an Air Force officer, flew many types of aircraft. I'm a graduate of the Air Force Test Pilot School and did a lot of leading edge development, test, and engineering work, and retired as a major general, eventually making my way back into the academic world. Why are we talking about tech transfer and collaborations? Well, this conference, Pivot, is all about the resurgence in geothermal, and it's largely driven by applying the oil and gas industry knowledge and technology to the geothermal world. But that's not the only source of transfer of technology. Military and space have historically been big drivers of innovation, but that's shifted from government-led projects to much more of a business startup innovation ecosystem. And that's exemplified here in Austin by the landing of Army Futures Command, AFWorks, and the Defense Innovation Unit in recent years. And these organizations are handing out significant amounts of non-dilutive funding to startups for innovation. We can get more into that as this panel goes on. We're also seeing a paradigm shift in space as commercial interest and related projects start to take the technological lead. This panel covers a huge range of diverse expertise, and I could easily fill an entire afternoon with questions for them, but we'll work within the time limit we have and incorporate audience questions as we move along. So with that, I'd like to ask each of the panelists to introduce themselves and the organization they're from, and also to briefly state as kind of an opening thing, what aspect of tech transfer or collaborations do they find particularly exciting at this time? And let's start off with Peter.
Hey, my name is Peter Boule. I'm a research science specialist at Aramco Americas. Aramco Americas is an independent subsidiary of Saudi Aramco. Much of the work that I do, I lead the efforts at Aramco Americas in well construction and the design of fluids and materials for building oil and gas wells. Prior to my work at Aramco, where I've been for 6 years, I was at Halliburton in cementing, and prior to that, at Johnson Space Center at NASA, doing work in nanocomposites and different kinds of nanomaterials. So my background is a combination of chemistry, materials science, and nanomaterials. And so I engaged in a lot of different kinds of research activities and collaborative activities between academia, government, and industry in building new ways of constructing wells or drilling wells. In particular, I like to see deployments of nanomaterial type chemistries in the field. So one of the aspects that I find to be particularly interesting in technology transfer from aerospace or from NASA into the geothermal field is really in composites and building high strength, high temperature resistant composites. I feel that these are much needed in geothermal wells as we're drilling to particularly high temperatures, and also the area of high temperature electronics is particularly interesting. Thank you.
Thank you. Welcome. Felipe.
Thanks, Ken. Really nice to be here with everybody. So I'm Felipe Teosi. I'm currently at the Jet Propulsion Laboratory, one of the NASA centers, of course, also run by Caltech. I'm a robotics technologist. What that means is we look mostly into the research world of robotics and sort of future missions to potentially make its way into space. I work in the extreme environment robotics group. So and like I said, sort of in the research arena there. So there's a plethora of projects that look sort of at Mars, some of it which is in collaboration with industry, oil and gas, fairly relevant, I think, to the space of geothermal. I would say adjacent because I don't particularly work right now on anything geothermal, and I hope that will change. Before JPL, I was at Chevron Corp, whom I think you gentlemen know. Chevron, I was there for about 9 years, also in the R&D world there, looking into sort of different projects for deep drilling, sort of high temperature, high pressure wells, in completions and the drilling world. Also, my academic background, a lot of my dissertation work looked into renewable energies, which is interesting to sort of hop back into this fluid structure interaction. How do we sort of harvest as much as we can from flow, looking into sort of vibration type mechanisms of structures. So I'm sort of a mixed bag, but I call myself a fluid mechanician that's jumped into robotics recently, or fairly recently, and it's been exciting. So happy to chat and glad to be here with you guys.
Got a particular area of tech transfer that gets you excited?
Oh, of course, yeah. So I think the exciting thing about, certainly to make geothermal ubiquitous is sort of reliable drilling, but doing it cheaply. So I'm excited about, temperature tolerant type technologies, both mechanical and electrical are exciting to me, but also sort of thinking through existing technologies and how we can sort of, mishmash these things together to make something work, something like an interesting refrigerator. So looking at the problem more from a systems level, and then bringing in collaboration from industry and bridging the gap with tech development and collaborating in that front.
Okay, thank you very much. Dave.
Yeah.
Hi, I'm Dave Ryan, co-founder and CEO of Navigo, a custom software science and engineering firm headquartered here in Austin, Texas. I'm delighted to be here and honored to join my esteemed panel of colleagues for today's discussion. And thank you, Ken, for the invitation. For over 25 years, Navigo has delivered custom software to the largest private and public institutions of the world with a focus on deep tech, high performance computing, as well as remote sensing and edge processing. We not only create software architectures and applications, but we also foster entrepreneurism by spinning up new ventures out of Navigo to keep our skills sharp on the bleeding edge. Navigo's spin-ups include a number of ventures to accelerate mapping of our oceans and space. And along the way, we've recognized opportunities and applying our skills in computer modeling and simulations, signal processing and telemetry to the subsurface, and have started a new venture focused on geothermal on a mission to accelerate mapping and exploration and characterization to the core of our Earth. We're most excited about opportunities for tech transfer to reduce cost and increase safety at geothermal E&P through state-of-the-art data lifecycle management and remote sensing and computer modeling and simulation. Thanks again.
Okay, thank you. Stoichi.
Ken, thanks for having me on here. It's truly blessing to have such a talented panel and to be here with you guys. And a little bit of background. So I'm currently the Defense Innovation Unit Southwest Regional Strategic Engagement Lead. Background, F-16 pilot, DARPA fellow, Stanford GSB grad, a founder of AFWorks, pilot trainee next, was the founder and leader of the Texas Military Department Joint Innovation Unit, as you know, and now currently leading the defense, commercial, and strategic engagement for DIU for the entire Southwest. A little bit about DIU, for those that don't know, DIU was created by the Secretary of Defense about 5.5 years ago to accelerate the commercial technology throughout the DoD, right? To transform the capabilities and the capacity and ultimately strengthen our national security base so that we can respond and answer our nation's call no matter what challenge we may face. In regards to what areas that we're really excited about, tech transfer along certain domains where a lot of the research and development is no longer coming from our primes nor our research labs. And these are particularly focused in autonomy, artificial intelligence, cyber, space, human systems, and now advanced energy and material. And so if I had to put a couple things, really excited about 3D printing, right? Both for part production, but also construction scale additive manufacturing, 3D printing of buildings. Who knew that was a thing? But there are lots of opportunities to do things faster, cheaper, and better. Atmospheric water generation. In regards to energy, whether it be geothermal, small nuclear, right all the way from the tactical level to an airman, a soldier, or guardsman on the front lines, all the way to installation resiliency. We just saw the winter apocalypse here in Texas, more than any other time in our life, with the amount of storms that are occurring, climate change. It is about resiliency, sustainability, and super excited about those fields that are coming from our commercial sector, like the Teslas, like Oklos of the world that are investing billions of dollars in this particular sector. So happy to take the conversation anywhere the community wants, and I'm glad to be here. Thanks for having me.
Okay, thank you, Stoichi. I don't remember, I didn't catch if you mentioned it, but he is a Lieutenant Colonel in the Air Force, and you'll have to ask him over a beer what Stoichi stands for.
Thanks,
okay, well, we'll start in with some questions here. I want to lead off with Stoichi. The military and NASA used to be the drivers and leaders in technology development, but now are frequently technology followers. But they also, as you've mentioned in the past few years, have really created a whole new ecosystem in innovation for the startup and small business world. How can entrepreneurs and startups plug into this system, and why should they?
Yeah, no, thanks for the question. Look, what is the problem that we're all trying to solve? Army Futures Command, right? Stood up a 4-star command in the middle of Austin. For the first time in 75 years, not even the Vietnam War motivated the Army to reorganize themselves. The Secretary of Defense created DIU. Secretary of the Air Force created AFWorks. Secretary of the Navy created Naval X. As a nation, we need to go faster. Our near peers, right, that are now peers like China, over the last 10 years have increased their defense budget by 10x. By 2030, they will surpass our GDP. They will surpass our defense budget. They will surpass our R&D budget. It's not just that doing things faster, cheaper, and better is a good way of doing business. We've really never had to, and now we do. In the future, this is going to be about contested logistics. We will not have free reign. We will not be able to have gasoline be able to flow into vehicles and planes and tanks and automobiles in that next fight. And so in order to be able to protect the country, we need to move faster. And so an element of that is you have to understand that back in the 50s, for every $1 in research and development we had, industry maybe had 50 cents. Now for every dollar we have, it's the Googles, the Apples, the Facebook, the Teslas that have now $11. It's the venture capital private equity community. And right, it's not spread equally throughout the nation, right? It's centered around Silicon Valley, Austin, Boston, and in the Northeast. And that's where DIU has offices. And that is the purpose of our organization, and where you'll find all of the other innovation unit, the whole DODX community, is to find ways to help our academia and industry to work alongside us. And so from that perspective, right, how can we help with contracting? How can we help with cybersecurity? How can we just make it easier to work with what is notoriously a very challenging bureaucracy? But at the end of the day, this comes down to our national security as a whole. And this is a whole of community, a whole of state, a whole of nation approach. Right, 20% of all the venture capital actually comes from China and Russia. They come to our businesses, they buy the technology, they use it against us on the battlefield today. And so part of it is an education process. Part of it is understanding some of those tactics. The 1,000 Talents program, a number of companies I've had to have a conversation with in the last few weeks. That professor they hired from a Texas university is actually on the payroll from the Chinese Ministry of Defense. That check that they were going to take from that Belgium VC actually came from a fund from Russia. These are things that most people are not aware of. And part of our organization is to help with that information, educate, right, the public, and create the propensity in the nation to want to work with us to make it easier. And so, right, for all of our security, whether it is responding to a hurricane disaster, humanitarian assistance for disaster relief efforts, domestic operations, or national security overseas, we need our companies to help our military go faster. Right? These technologies are not coming from primarily the Lockheed Martins and the Boeings of the world. Right? Things on cybersecurity, right? The Colonial Pipeline that just got shot down, right? The small drones that take out 5% of the world's oil in Saudi Arabia. These companies, these technologies, they're not walking down the halls of the Pentagon or the National Guard Bureau or any one of our DoD partners. And so our passion is to help those companies work with us. And so if you go to www.diu.mil, we have a website. It's a very easy process. We have a very to easy understand. We start with a government problem. We know where the problems of the money are. We put on a 1 to 2 paragraph explanation of the problem. All we ask is a 15-page slide deck. That's it. And from there, we then invite you for a Shark Tank-like pitch. And from there, we go commercial pricing with commercial IP rights, and off to the races we go. And from when we post it on the website to award of contract, our aim is 60 to 90 days. So happy to take any other follow-up questions from that.
Okay, thank you very much. And truth in advertising, I am currently funded by an AFWorks grant, very similar to the Defense Innovation Unit, along with Sage Geosystems, who's spoken in this conference. It's a funding that deliberately pairs an academic institution with a startup. And in this case, the subject is studying and designing a geothermal power system to put in on the south side of Houston at a small military base there.
Absolutely. There's several pots of money like Small Business Innovation Research, SBIR, and Science Technology Transfer Research Grants, STTR, and a number of other pots that are out there. And the goal of all of these innovation organizations, AFWorks and Army Applications Lab and NavalX and DIU and Ensign, is to help play the Sherpa role so that you can help navigate to those non-dilutive pots of money that can actually get you customer experience and help you as a company look at the DoD as a vertical where maybe previously you would have not.
And to why an entrepreneur should pursue this capital is some really important points, I think, for the private sector to recognize that this is non-dilutive capital, so you're not selling equity. It is literally a way to fund customer discovery, and not just within the DoD, but the broader US government. And a big challenge with selling to the government is navigating regulation for federal acquisition. And Stoichi has been incredibly helpful to our ventures in that regard, and his colleagues within government are looking for ways to foster innovation and engage the private sector, especially small business, to include companies I've been involved with that have enabled teaming opportunities to subcontract partners with skills that we do not specifically have, but collectively we can offer something that no one else could, that is in competition with a large prime vendor that is a traditional contractor to government today.
Yeah, thanks, Dave. Appreciate it.
Thank you. That was a good start. Peter, for you, what immediate benefits could high temperature drilling and production reap from interdisciplinary collaboration and tech transfer? What do you see on near horizon?
Right. Yeah. Thank you for the question. I see the highest TRL, of course, transferring most quickly. And so, for example, in ablators, materials where you've got particularly, well, actually in thermal protective systems, so non-ablative thermal protection systems, where you've got extremely high temperature tolerances, 1500, 2000 degrees C. These kinds of systems are the kinds that enable our robotics missions on Mars, the kind that enable the solar mission, the Parker solar probe, the kind of work where you're designing lightweight thermal protective systems, for instance, where you're foaming these kinds of resinous materials, making porous carbons, which serve this kind of thermal protective, serve as a kind of thermal protection barrier that protect entire spacecraft from extraordinarily high fluxes of heat. And these kinds of things are prime candidates for wells and for coatings of tubulars, casing in a deep geothermal environment where you've got exposure to brines, where you've got exposure to potentially geothermal wells have many problems with sour gas, acidic corrosive environments, which are known to lead to casing collapse and very, very expensive problems. And I think that a lot of the work, a lot of the really brilliant work that has been developed at NASA in TPS is very applicable to that space. And that's probably the highest TRL, but I think there are many, many other exciting opportunities in further developing that kind of technology, which can bring us more efficiency inside of the geothermal space, especially when you start looking into things like 3D printing. And you start looking into ways of improving the thermal capabilities of materials in the downhole environment. A lot of the time people think of 3D printing as something where you can easily transport materials from one side of the world to the other just by sending a data file. But it's much more than that, because 3D printing gives you this power over the placement of materials with respect to each other. And composites are typically multi-layer materials, multi-material materials. And the fact is with 3D printing, you have it's just an enormous amount of control over the placement of materials with respect to each other. So you can really move towards materials that have high toughness, sort of simulating the effects of hard and soft components, just as you see in nature with mother of pearl, nacre, with shells and materials that we can take lessons from and perhaps build better materials that are out there in nature and use them to build wells, successful geothermal wells for these really high temperature environments.
And use the term TRL a couple of times, just in case some people in the audience are familiar with that. Technology readiness levels, a relatively standardized scale from from 1 being a bright idea or 0 to 9 being production ready, tested prototypes. It's a fairly common scale for technology development.
Yeah. So sorry, go ahead.
Go ahead, Peter.
Oh, I was just going to say, so for example, the non-ablative systems would be a TRL 9 level, whereas the 3D printing systems could be a little bit lower than that. For instance, TRL 5 or so. But within a few years, I think these kinds of systems could be field ready.
Okay, Felipe, let's take this into space. What's some overlap between space environments and downhole environments?
Sure, Ken. Yeah, I was just gonna say, TRL 5 or 6 is proven in the environment, but not quite ready for production, right, Peter? So, and I should also start out with a brief disclaimer here. I'm certainly I'm at JPL and I work for JPL, but today I'm here as Felipe. So a lot of these things are my personal opinion. So I have to let you guys know this sort of a priori here before starting. But I do think there's some interesting places where I'll say requirements or desirements, if you will, overlap with geothermal. I think the one that sort of comes to mind front and center is Venus, just because it's in the high temperature domain. It's I think surface temperatures are on the order of 460 C, fairly high pressure, 95, 90 bar, so 1500 psi, and it's CO2, which working fluids for geothermal, CO2 is one of the candidates there. So supercritical CO2 is rampant, and so perhaps tackling a lot of these, and it's got some sulfur in it too. The atmosphere that's Venus. So if you want to try and tackle some of the things, material-wise, like Peter was talking about, there's a lot of similarities between the Venus environment and a downhole geothermal well. And so then the next question is, what are some of the technologies that potentially could cross over between these two? I'll say a space application, say a lander or a probe, and something downhole, perhaps some rotary steerable tool, or some interesting measurement while drilling tool. And I think there's a lot there. Although I will say, I think we worked on a concept for a long-lived lander a couple years ago. It was just a concept that we presented at an AGU conference, and there's a lot of room still to be developed. So I think Peter touched on some of the TRL9 items on the materials world. There's a lot of sort of TRL3, 4, 5, even 2, that needs to be pushed up into the higher numbers. So things like motors or generators. There's a lot of effort. I think that folks I know at Honeybee have done at JPL. They've also pursued some of those technologies. So the question then becomes, how do you sort of push those things forward in the TRL space? Sort of as one way to broach this problem. Of course, it takes a while, and to get those things up to the higher level TRLs, and perhaps Stoichi is trying to make that quicker with the 90-day turnaround on some of these proposals. But another way of looking at this perhaps is looking at some of the TRL9 things and trying to see where in the Venn diagram do we fall, and is there anything that we can sort of piece together into an engineering system that can satisfy either a large segment or maybe 90% of those requirements, and still give us something useful. And I perhaps I think we looked at some thermoelectric coolers. Things have gotten a lot better nowadays, relative to 10-15 years ago, as far as cooling using sort of thermoelectric materials. Can we sort of frame something that would give us a refrigerator that cools down the electronics, or a subset of the electronics that lets us do what we need to do downhole to make this sort of efficient and cheap, but also reliable at the same time. So those are the sort of the same challenges there, because a Venus lander would need a similar approach, and you don't want to be launching. In fact, it'd be very tough for you to launch anything TRL below 6 anywhere. So those are the challenges. Then how do you take something that's TRL9 sort of ready to go, assemble it into a system that is shown or proven to work here on Earth, and then you sort of push it out. So anyway, all that to say, I think Venus is a good target there. I think there are other places with pretty high pressure system, like if you're looking at probes for Uranus, which we did, you can get up to pretty high pressures there, 500 plus bar on some of the lower clouds. So yeah, technology that would sort of filter into these types of applications in space, I think would fare well to be transferred into the geothermal world.
Yeah, I think the point is that, we need to be looking for technology that can be cross-applied no matter where it's coming from. And even in space, as you mentioned, there's environments that are pretty demanding. There's also sun grazing probes that have to survive high temperatures and such. And we saw earlier today, we had a space pioneer who just returned. And there's all this commercial space, which is going to further push that technology development. And I'd also throw in kind of trans space, the hypersonic world, where you again need sensors and other equipment that can survive a very high temperature, high pressure, high vibration load environment, which really is something we haven't talked about much yet. So let me go to some audience questions here, and I'll throw these open to anyone on the panel who wants to jump in. We've heard on a few panels, startups talking about partnerships with national labs and NASA on tech transfer. How easy is this to do in practice?
I could speak
$1
to
million
that.
question. Yeah. Go ahead.
Yeah, absolutely. That the key words for engaging NASA, I think, are Space Act agreements, which is a recognition of the government that they are not good at commercializing their own innovations or specifically their patents. Government intellectual property for commercial use is sitting on the shelf waiting for industry engagement. There are a large number of high quality patents granted to the US government, and engaging through Space Act agreements is a great way to transfer that technology. And independent of that, there is, while NASA does not qualify as a federally funded research institution, other labs such as in the DOE and academic institutions would qualify for STTR. And that being—
So David, let me just say,
Yes.
JPL is an FFRDC. We're the 1 out of the 10 NASA
That's right.
center that is, yeah. So anyway, just to quickly throw that in there.
Yeah,
The odd
absolutely.
man out.
And then there's just general MOUs, Memorandum of Understanding equivalents, like CRADAs, that stand for Cooperative Research and Development Agreements, that largely are not going to transact dollars or rights, but instead will just be a handshake for you to work with a government institution. But I'll hand it back to the group.
Yeah, I can pick off of that too, David, if that's okay, or Ken. I guess to the point of how realistic is that, I think personally I've worked on a number of commercial industry collaborations here at GPL, and in fact I manage a project currently with a collaborator. So it's feasible. Some of the challenges that come with a Space Act agreement is demonstrating, one, that whoever you're doing the Space Act, whichever center you're working with, is in our case at JPL, that we're solely positioned to work on that technology, and two, that the technology space that you're pursuing is well aligned with the NASA's technology roadmap. And so you have to sort of prove that everything is well aligned. Otherwise, how do you justify resources being diverted from any particular NASA specific project to do something for industry? So it's much I guess the main thing to think about is that it's NASA, certainly being an agency, we're not a service center, so it's not like someone can just knock and say, work on this for me, please. You sort of have to convince NASA that we'd be working on it anyway, but there's an opportunity here that we can work on it together and sort of leverage off of the fact that this is then commercializable and propels the economy, et cetera. And so I think that's the trick. And I think my understanding is that it oscillates how often, if there's a lot of work, that oftentimes NASA has a lot of projects that are pushed onto JPL, for example, and so there's pressure to sort of keep the commercial work down, and so it's a bit more difficult to convince NASA that we have the time to spend on commercial projects. whereas other years it's not so bad. So I think it's realistic. One needs to work at it and sort of understand that it takes a little bit of time, but it's very much possible. And I can say that I've worked on, and I'm currently working on a few.
Yeah, let me piggyback on Felipe there. Two organizations that I would point people to help support them. One is FedTech, and I posted the link in the chat there. They're a nonprofit organization that is actually funded by the government for tech transfer, and they will help be your Sherpa to across NASA, the Air Force, right, and the rest of the DoD entities. A lot of the research and development that's coming out of our FFRDCs to help commercialize that is the ethos, that is the theory, that is the thing they put their life force into as an organization. So I would help point you to FedTech. DIU has 3 organizations that comprise DIU. One of them is NSIN, the National Security Innovation Network. And this is about, as an aspect, they also focus on taking what is in academia as well as in the FRDCs and help spin out companies and help support those companies and help them get access to some of those research grants that we've been talking to SBR and STTR across the joint services. And so NSIN is another organization I would point you to. They have a lot of great programming. There are regional directors, reach out to them. They are fantastic to work with, and they have a lot of funding from the Secretary of Defense to get after this very question, to help companies like that ask the question, how do they get after it?
And I would also point out that other countries either have or are working along similar lines, speeding up innovation, as everyone finds that business and startups are pretty darn quick and agile.
And that's actually a key point. One of the elements of DIU is now we're broadening out to our coalition partners, right? The National Guard that has 89 state partnership programs that are out there. Even Texas just has, Egypt, Czech Republic, and Chile. But there are 89 different countries. We're working with NATO, right? This is about interoperability and enabling our partners to be able to gain access to the technology within the United States. I mean, there's a finer point here that I just want to highlight. China is not resting on their laurels. In many ways, there is a very large influence campaign, right? Climate change, and very much blaming, right, the United States for a vast majority, but hey, we have a solution. And so it is very important as a nation, as a community, to be able to work with our coalition partners and help do that tech transfer, not just within the nation and across our DoD joint services, but our international coalition partners as well.
Okay, another audience question here. We're getting a lot of them coming in now, just a minute. Is a very direct question. What are the limits on temperature for electronics developed in space versus downhole at this point? I don't know if Peter or Felipe would like to jump in on that. I've heard some in this conference already.
I would say, I am not an electrical engineer. I am working adjacent to a lot of these things. But so, I guess the famous, don't quote me on this, but it seems to be somewhere around, 200 C, 250, where things start to break down, things like memory. I guess I'm talking about, this is a very general number that I'm literally just throwing out there. So if you want to get an idea, I think, some folks are much better positioned to answer this than me. But if you just want to think through, and perhaps for the sake of discussion here, I'd say somewhere around that. And then you can sort of try and push that further for, more analog type things. And I know folks at, I believe Goddard have worked on some things that are, pushing 460 plus. I know folks at JPL have done the same thing for capacitors, et cetera. So yeah, anyway, whatever that's worth, but I'd say talk to other people about that. If anyone else here on the panel wants to take a crack.
Yeah, well, so for batteries, the lithium thionyl chloride batteries, they advertised, the commercially available ones will say up to 200 C Realistically, though, their best performance is lower temperature than that. Once you kind of get above that amount, then it starts to become more of research and researching the newest materials. And so it's a little bit less available. I think inside of a lot of logging tools, what they'll do is thermally insulate, sometimes vacuum thermally insulate the materials so that they don't have to have the electronics experience the actual temperatures that of the environment that they're measuring. So
and then you have to run them quick, right, Peter? You gotta.
Yeah, that's right. That's right. So
in and out.
It's an example of an area with a lot of challenge still.
Yeah.
Yep. During my graduate work, I did a lot of well logging with a Dewar Flast tool, and you could stay in a pretty hot zone for, a few hours.
Yeah.
Also, we do have a sensor development group here, and you brought up something, Peter, I think is pretty important. When you're talking about the high temperature electronics, it breaks down into different components that have different levels. So you've got the batteries as, one set, you've got the sensor, you've got the chip,
Yeah.
you've got the memory components, and all those can have different things. And so it's an in parallel development to try to get all those up to a common usable temperature limit, like we've heard needed before by several speakers who've laid out, 225 is a good starting point, 300 is an ideal, and so on.
Right. And if you have sensors on your composites, for example, doing some kind of structural health monitoring, you want those not to interfere with the mechanical properties of the composites. And it does become complex. But I think there's a lot of work now that's in the research domain where people are looking at bringing sensors directly into composite materials. So being able to measure resistive changes in materials inside of the composite. So the composite itself conducts electricity in a certain way that makes it somewhat piezo responsive. So you can measure small impacts and that kind of thing. But that's still something that's kind of an emerging kind of technology.
Ken, if I can, and this is sort of, I think you sort of, you have a subset of these electronics per se that are TRL9 and can survive fairly hot things. And then you have things like memory and the chip that won't. And so the question becomes, do we take the time to then mature these technologies to get them up to 400 or 300 and change, I guess, is the goal. Or, can you do something where you have an active cooling system and take the time to, at least in the while we're pursuing this primary goal, where we can get somewhere with an active cooling type system using off-the-shelf, albeit more robust electronics. And so I think that's an interesting challenge and to think about, and perhaps where folks either in the audience or here in the group can speculate as to what can be collaborated where.
Okay. Are there instances that any of you can think of where defense or space testing facilities and equipment can be utilized to simulate the downhole conditions, and how would outside entities access these? I don't know where to start on that one, but it's an interesting question.
So I can say we, for example, we have a Venus chamber at JPL, right, where we try to do a lot of these tests. We've done, some testing that gets up to Venus conditions and still pretty hot in pretty high pressures. So yeah, I think that's where you'd start. I am hard pressed to think of a place where you can do multi-phase flow at pressure, temperature. Pressure is greater than 5,000 plus psi with flow in multi-phase. I think that's a challenge. I don't know of a place that can do that per se. That's not to say it doesn't exist. So, but yeah, certainly, if you're trying to do static, pressure, temperature, I think there are a number of places. In fact, I think Peter might have some purview into some of the Halliburton items. I know vendors service companies for oil and gas have a lot of those facilities. I know we have some, like I said here, JPL. I think Goddard has one also for the Venus set conditions. And so to access the ones at NASA, I think you would need something like a Space Act agreement. Otherwise, I think collaboration, partnership with companies is also another way to go.
Do CRADAs apply to NASA facilities? Dave, can you answer that one?
We've not engaged with a CRADA with NASA specifically. I would look otherwise into the DOE and NREL, where open source, simulation platforms are being, or should say, simulation platforms are being open sourced, or at least that's the goal at Navigo for us and working with those institutions. But I think Felipe's right. It's going to be a Space Act, either probably a non-reimbursable Space Act to be specific about it.
Okay.
Yeah, I mean, we have a number of facilities at Aramco for measuring materials and their mechanical properties under pressure. Sometimes we go to the Department of Energy, to some of the national labs. They have great beam lines for X-rays, which help us to study mineralogical transformations in cements at high temperatures. And those can be quite useful. I expect also some NASA partners in looking at the effects of radiation can also somehow be transferred to material studies as well for downhole.
Yeah, I should say Southwest Research in San Antonio has many of those facilities.
Good point.
Good point. And they have spoken, I believe, already on the conference some too, and are involved in some geothermal projects. Are there specific examples out of hypersonics research that could be interesting for geothermal problem sets? Does anyone have any thoughts on that? I kind of brought that up earlier, but I don't know if anyone else has looked at that area. While you're thinking about it, the main things, as I already said, that I think transfer immediately from hypersonics is, one, you've got a high temperature regime, but two, it's a very high dynamic load vibration regime. So I think I'm not an expert in this. I'm not a drilling engineer, but if you're looking at improving drill stem electronics and sensors, there could be some interesting crossover there. Also, when you're moving at hypersonics, you tend to have an ionization cone around you. So you've got to find alternate ways to communicate other than electromagnetic. So that's an interesting area too. Any other thoughts on hypersonic activity?
I don't have any additional, I just wanted to second here. I agree with you that I think the high temperature is what makes it interesting. Albeit I think a lot of the hypersonic items tend to be, I guess, short-lived, and short is relative. But again, these wells may not, you might have a flow through time and a turnaround of hours, maybe single-digit days. So I think there's crossover there.
I think the composites area, again, is kind of an interesting area for hypersonics. And also, for instance, there was a time at NASA that we were looking at doing in situ repairs with pre-ceramic polymers. And we'd use these to convert to ceramics on re-entry. So that was something for looking at the shuttle for leading edge of the wing after the Columbia shuttle disaster. But so some of these kinds of maybe a little bit different, but these kinds of ways of using ceramics, but in a repair sort of sense, may be interesting for example, remedial work in geothermal wells.
Interesting thoughts there on the materials side. And I know there's a lot of work being done on self-healing materials. I don't know how high the temperatures go on that. What about sensing from space? One of the audience members says they understand there's a geothermal temperature characterization project from the ISS right now. And of course, we've been doing resource mapping, both terrestrial and extraterrestrially for a while. So where does that stand? Anything on that?
So one thought that I don't know specifically about the ISS experiment. I do feel like, you know, if we were to collaborate, you know, a lot of these things as far as remote sensing for, you know, other planets or moons, you know, it's because we don't have access to them. But a lot of the modeling technology to sort of pinpoint based on some of the remote sensing measurements, I think that's very robust and certainly applicable to Earth. And I say that in a, you know, just on Earth, we just have access to the Earth, and so, you know, there might be you know, some better types of technology that could be used for more precise measurements, for example. But you know, yeah, I don't know anything specific, but I would say, you know, certainly on the modeling side of this, which I think is the complement to any remote sensing type of experiment, I think it's something that we can that there seems to be opportunity there, or at least I think so.
And I would point out that it's not just thermal sensing that applies. There's a lot of cross flow using satellite-based radars, particularly inverse synthetic aperture radar, for precise measurements of changes in the Earth's surface that have been particularly useful, I believe, to monitoring of ongoing geothermal systems, and to some extent exploring for the right tectonic regimes too. A specific question. Oh, go ahead, Peter.
Yeah, I was going to say, in oil and gas, there had been this kind of a vision for, and a number of different projects sort of came about from this vision of being able to visualize in real time what your well looked like on your phone. And so you would have the appropriate sensor system that would be relaying information to you. And of course, that's very much a kind of a pie in the sky kind of dream, but smaller increments towards that are possible and are being explored. I would imagine that a lot of work over in aerospace would help bear more fruit in that direction.
Peter, a specific question for you, kind of along those lines. What are your top 3 material science challenges that need to be solved to enable hotter drilling?
Well, so I kind of, in terms of wells, I focus largely on the construction side with cements. And one of the areas inside of cements is getting cements so that we can get to temperatures above 500 Fahrenheit, you know, so that we can, and there are systems. There's a really nice cement system that was developed over at Brookhaven National Lab on calcium aluminates, which does a really good job of this. But the problem is inside of oil and gas, there's not a whole lot of market above 500 Fahrenheit. So there's not a lot that's been developed in terms of the additive chemistry. And so the additive chemistry for constructing wells is, you know, it's maybe arguably it's about 75% of what you need, right? You have to have all of the systems that will make the cement pumpable, that you can that you can use to change the mechanical properties of the cement to be suitable, that can basically prevent influxes of fluid from rock formations as you lose the hydrostatic head as your cement's building gel strength. So all of these different kinds of things above 500 Fahrenheit kind of need to be developed out, and I think that's going to be very important. And also there's an aspect of drilling where if you're drilling at really, really high temperatures, often you're dealing with sour gas, poisonous sour gas. You have to not only worry about corrosion, but the safety of your crew. You've got to worry about the polymers inside of the drilling fluid degrading. And so often they'll underweight their fluids, so they get an excess of material coming from the rocks and rising to the surface. So there are certain drilling challenges there beyond just the challenges in the drill string, and perhaps needing to move towards more composite drill strings to resist the corrosive environment of those temperatures. So I think those are very important, but I also think this sensing is important, and being able to save a lot of money if you can sense problems or issues before they become major problems inside of the well, where you can do corrective actions. I think those areas are probably some of the most important areas to address.
And Ken, let me take that question in a different direction. Like, what are some of the challenges to energy as a whole from what the government is really focusing on? Right, for us, we have these challenges, one, around as we are electrifying everything because of the concern about logistics and contested logistics of being able to get, gas to planes, tanks, automobiles in very difficult environments. One is we need to be able to charge, right, these systems, vehicles, planes, whatever. Right now, we're looking at about 2.5 megawatts in 15 minutes. The second piece is around battery certification, right? We just see Tesla vehicles that run into a tree and explode because of lithium-ion batteries and the danger. We need to have other energy sources or other different, battery chemistries that allow us to be able to realize that dream that we'd like to get to, which is full hybridization of vehicles, electrification of vehicles, being able to charge from vehicles to installation from geothermal into those vehicles. And then lastly is really about a supply chain issue, that most of these lithium ion batteries, right, are heavy metals, right? And so part of it is this new chemistry, but looking at alternative sources at a installation source like geothermal that can then power, right, a lot of the other accoutrements that will enable, right, this new paradigm. So just for those people in international, just understanding the challenges that we face, we are hoping that these are problems that are solved by the commercial sector, but right now that is not the case. I cannot charge 2.5 megawatts into my vehicle in 15 minutes. And so these are things that we're looking for universities and companies to hopefully, help us solve those big challenges.
Okay. All right. We're going to wrap up here and give each of you a quick minute to close up and include, again, what gets you excited about this area. And let's go first to Peter.
Well, I want to thank you for having me on the panel. It's been a pleasure. It's great to talk with everybody. And well, I suppose, yeah, when you're talking about a real materials challenge, you're pushing the frontiers of what's possible. And for this, there's going to be a combination of tech transfer that's going to enable things that haven't been able to be done before. And there's also plenty of opportunity that I believe will come about from going to these really, really hot environments, especially when you're looking at closed loop geothermal, where you need to get hotter to get more power in your geothermal power plants. So I think it's a very exciting challenge, and there's plenty to do in the domain for material scientists.
Agreed. And we've only just barely scratched the surface here. We didn't even get into nanoparticles, nanomaterials, and what they can do.
Right.
That's a whole other panel. Felipe.
Yeah, to second that, Ken, thank you so much for having me. It's been a real pleasure being in this panel with amazing, smart people and a great discussion. And I think what excites me is that it's to piggyback off of Peter here, it's a challenge. It's a very hard problem that hasn't been solved yet. And I think as an engineer, it's the fun kind of problem to have. It's the challenging one. And I think it's one that could potentially have amazing impact to our future, our energy infrastructure. And so those two things combined make it very exciting. And I think particularly for me, I enjoy, the fluids challenge, the mechanical and the electronics challenge, and getting those things sort of up and running in a system to get geothermal wells drilled. Yep, very exciting. And potentially, I mean, I know this is an interest of yours, but, it'd be very interesting, Ken, to have a geothermal somewhere else, maybe the moons of Saturn one day. I know it's just a delta T, and there's a big delta T from surface to liquid ocean. So that's also very exciting, although very far-fetched and far off, and that makes it even better.
It may need to be sooner. We're not that far away from sending people further out, and we'll need a power source. And
Absolutely.
I could go on to that one for hours. Dave.
Ken, thanks again for inviting me to this panel. Congratulations to the Texas Geo team, and especially Dr. Jamie Beard for her magnificent work on year 2 of this conference. It's really been amazing. In closing, I want to encourage all to begin iterating on how to reduce future CapEx and OpEx for geothermal energy production through data access and quality control and improved resolution of our subsurface. This is going to be the foundation of higher quality computer modeling and simulation to reduce cost and improve safety. And additionally, we have an opportunity to not only learn from the large representation here of oil and gas, but also from ocean and space exploration and characterization to advance our edge processing for prioritized delivery of high value data in near real time, rather than waiting for raw data to be physically delivered via sneaker net. There's an example of tech transfer at Felipe's colleagues and our partners at NASA Ames, where they have optically imaged seabed for coral and stromatolite research, and those then use that data to train deep learning models to search for life on Mars, as though there might be a way to pattern match, for example, and recognize those objects. And I think we need to keep our minds open about tech transfer and how this might enhance our ability to automate and scale geothermal at a faster pace towards what eventually will become economic viability. Thanks again.
Okay, thanks, Dave. Stoichi. Oh, there you go.
Yeah, just real quick. Thanks for being on the panel. Look, this is a monster problem of energy resiliency. Geothermal is going to be a critical element to that. Take advantage of the resources that we have to help inspire, gauge, and support academia and businesses to help us move faster, from FedTech to Ensign to DIU. And looking forward to participating in the ecosystem and being here for the community to help us tackle some of the largest challenges that we have around sustainability and energy resiliency. Thanks, Ken.
Okay, well, thanks to everyone on the panel. This has been fun. It feels way too brief, but hopefully we've done a little bit to open people's aperture on how to apply technology from one domain to another, how to other than traditional sources for funding and such. Again, my thanks to Jamie Beard and her helpful staff who've put this together for an even better second year of Pivot. I'm looking forward to next year. And everyone have a good rest of your day. Thank you much.
Thank you.
Thanks again.